In today's video, I'm going to talk about vectors. And vectors are things which express magnitude and direction. They're one of those areas in which algebra and geometry and even things like physics can intersect. So let's get started. A vector has both magnitude, meaning strength, or strength, and direction. A vector is represented by an arrow and looks like a ray from geometry. So this symbol represents a vector that has a starting point at A and moving towards this point B. So that's how we express direction. The starting point and then ending point. So you could also just give a vector a single letter for a name, like U or V, instead of naming the starting and ending point underneath that arrow. Alright, so we want to find a vector that represents the movement from point -1, 2 to point 3, 3. So -1, 2 would start us right here. 3, 3 would end us right here. So the vector is going to be traveling in this direction. We use an arrow to indicate that it's traveling from here and going in that direction. Now we can add and subtract vectors. To add together vector u and v, you put the beginning point of v at the ending point of u, and then the sum of the vectors would go from the beginning of u to the ending of v. So, for example, to draw the sum of u and v down here, we would take this u and we would put it, we would take this v and put it at the end of u. So essentially, whoops, those are together. Go back here. So we would take this v and lift it, put it up here at the end of u. So we take that and be about this long here, that v is. And so u plus v would be, give it a different color, u plus v would go like this. Now it should be a straight line, but it would begin at the beginning point of u and end at the ending point of v. So that would be u plus v in red. Now we can also scale vectors. Scaling vectors is essentially keeping the direction the same, but changing the magnitude. So this vector would be 3 times the strength of just regular u, because we have 3 as that constant in front. So we take it and we're going to make it 3 times the power. So we're going to add 1, that's about the same length, and then another one. Sorry, this tablet, it's pretty hard to draw straight lines. Could probably find another way to do it, but I think you get the point. So this would be in red. So this whole thing would be a single vector. I'm going to do it in green over top all of them. 3 times as long. So this would be 3u. To scale a vector by a negative, this negative is going to change the direction. So it's going to have the same strength, but opposite direction. Like so. All right. Next, to subtract vectors. See where we are. Subtract vectors, we think of it this way. think of subtraction as adding the opposite. So, so we're going to put the beginning point of v up here at the ending point of u, but we're going to need to go in the opposite direction because that negative changes the direction of v. So instead of going this way, we would go the opposite direction. Put this that way. And so then, our final vector would start at the beginning of u and end at the ending point of negative v. So something like that. Should be u minus v. So I'm going to pause the video here and let you do this one on your own. As you can see here, I tripled the magnitude of vector u, and that gave us 3 times u. And then I went in the opposite direction and tried to double the magnitude of vector u, making negative 2 times u. As you can see, I didn't quite have enough space, but you get the idea. Next up, it's most useful to represent a vector using length and a particular angle, theta, measured from standard position. So, for example, if we had this vector u, we would measure the angle starting at the positive x-axis, and that angle we'd call our angle theta. Another note that I like to make is that a vector of length 1 is called a unit vector. Just like a unit circle is a circle with a radius 1, a unit vector is a vector with a length of 1. Next, how to write the component form of a vector. So, the vector x, y, and these are sort of pointed parentheses. They're not like the regular parentheses for Cartesian coordinates or for polar coordinates. They help us know that this is a vector that we're talking about. So it has a starting point of 0, 0, and an ending point at x, y. And so the vector 3, 4 would have a starting point of 0, 0, and an ending point of 3, 4. And so then this vector would go up and to the right and in this direction. So next, we want to find the component form for a vector that's 5 units long and that's at an angle of 135 degrees. So look at this off the bat, and I know that this is going to be somewhere over here because 135 degrees is going to put us in quadrant 2. So there's a couple, I think, ways that you can do this, but one of them would be to use the polar conversions, where x equals r cosine theta and y equals r times the sine of theta. So then, since the length of the vector is 5, then we essentially have a radius of 5, because we're going to be 5 units away from the origin here. Next, we would do the cosine of 135 degrees. 135 degrees is 3 pi over 4 in radians. So we do the cosine of 3 pi over 4. And then, oh, just hold on one moment, please. I'm sorry about that. There was somebody at the classroom door. Alright, getting back to things. We've got our sine of theta, which would be 5 times the sine of our angle, 135 degrees. So, the cosine of 3 pi over 4 is going to be negative root 2 over 2. And the sine is positive root 2 over 2. So we'll multiply those together, and we're going to get negative 5 root 2 over 2, for our x and positive 5 root 2 over 2 for the y. So we know that our point, our ending point if we were to graph it, would be somewhere, over here in quadrant 2. So it would be a ray starting here and going out in that direction. Next up, we're given the vector and we want to find the magnitude of that vector and then the angle that helps create it. So we have a vector in standard position, so it starts at the origin. It's going to go 3 to the right and 2 down. It's going to look something like that. So we want to find the magnitude of this vector. In other words, how long is this vector? So to find that, I can use Pythagorean theorem, because I know that I can make a right triangle like so. The x coordinate would be 3, the y coordinate's -2. So I can square those and get 9 plus 4 equals c squared. That'll give me 13 equals c squared. So my hypotenuse is going to be the square root of 13. And so that distance, that magnitude, is the square root of 13. So I'm going to write that. Magnitude. Root 13. Next, we need to find our angle. So our angles are measured in standard position. So we start at the positive x-axis, and we want to see what's going to take us over to our ray. So that's going to be what our theta is. So there's a couple of ways you can do this, but I'm going to have us use inverse tangent. So let me get this pen out. So we have inverse tangent. Ultimately, we'll use inverse tangent, but we have to set it up as a tangent equation first. So whatever this angle is, we know that its tangent is going to be y over x. My y is -2, and my x is 3. So that's going to be -2/3. So I want to know which angle has this for a tangent. So let's use tangent inverse to do that. Tangent inverse of -2/3, that equals -33.7 degrees. Now we want a positive angle though, because in standard position we're going counterclockwise around. So if this angle here, let me put this in blue, if this angle here is, oops, that looks funky, that's a little better. If this angle here is -33.7 degrees, then this green angle is going to be 360 minus 33.7 degrees, which would give us 326.3 degrees for our theta. All right, see you in class.